All right, so welcome back from your summer break. I already recognize quite a few faces, so I think most of you were in my fluids class. I'm sorry, in my thermal class. You're in my fluids class this quarter. So who wasn't in my thermal class and therefore doesn't know about? Keep it up, keep it up, keep it up. Just to get an idea. All right, maybe 15 or so of you. Well, you'll probably very quickly get used to my style. Let me go over a few administrative issues regarding the course. I'm sure everybody knows that we're going to meet here Monday, Wednesdays, and Fridays from 12 to 12:50. As you can see, I pretty much had to ask the previous instructor to leave, just because it takes some time to get everything set up. So at the same time, I want to ask you to make sure that you come in. Try to be here a couple of minutes before 12 so that everybody is in and seated. Not now like those three over there that are coming in late, but try to get here about 2 or 3 minutes earlier. Presumably your previous class lets out on time and gives you time to walk here and be here on time. That way, because we only have 50 minutes, the lecture is pretty short. We're able to get through the material that we're supposed to get through. Then there are discussions which are going to be on Mondays. So this coming Monday, there is a discussion. So make sure you go to discussion. There are 4 sections. Starting at 1 o'clock, so 50 minutes each. You must go to the section you are registered for. That is, if you didn't get space in the 1 o'clock, which is the one that you wanted, and you are in the 4 o'clock, you still have to go to the 4 o'clock. The reason is very simple. We're going to be using the iClicker like we did in thermal, but the iClicker is going to be active for you in the section that you're enrolled in. And the reason we're doing that is because there was a problem last quarter with a lot of the students showing up, say, in the first couple of discussion sections, and then the students who actually weren't enrolled in that section would walk in and the room was full. They couldn't find a place to sit. So you must go to your discussion section. The TAs, you remember Franz? Actually Franz, even though Franz is listed here, just because he's going to be helping a little bit with the class, the TAs are Ya, Lou, and Doreen. You do remember Doreen from thermo, I guess. So Ya and Doreen are going to be your TAs. The text is the one by Munson. If you go to the EEE website for the course, I put a link there to the Wiley website where you can decide which version of the book to buy. And I don't really force you to buy a text. The only reason you need to at least know what is in the text is because of the homework problems that are assigned correspond to the numbers in this edition, which is the 7th edition. So if you're working with the 6th edition of the book, the problem numbers will not match. So you make sure that you have the right problem numbers when you do the homework. Now, it's a good idea to buy the book. You're going to be using it in 130A and 130B, unlike what happened with thermal. Most of you are in 115 also? You're not? Yeah, so unfortunately, you're not going to be using the same book that I used for thermal. So we'll try to work that out, but it's not going to happen this year. But this one, you're going to use it both in 130 and 130B. Wiley also has a very nice website that helps you study. You can, if you buy what they call the All Access Pack, you can download the book to your tablet, your laptop, and you can also access, practice problems and get solutions and, random questions like I do in class with the clicker. So I think it's a good thing to have for your own education. The breakdown of the grading is right here. Maybe I'll blow this up a little bit. Very similar to thermo, except that we have 2 midterms instead of 1. So there will be 2 midterms, a final exam, then your homework, and the participation as measured by the iClicker responses. The homework is the same method that I use in thermo. That is, you have to, particularly if you didn't take a class, for the transfer students. Are there any here? First quarter at UCI? So you have to go to this, see if I have it here. It's not here, but if you go to the EEE website of the course, there is a link there to the learn.uci.edu website where you have to register for this class there. So you have to go there and register for fluids under the Learn, which is part of the extension. And we use that to turn in the homework. So the homework you just upload as a PDF file to that website by the deadline. And that moves things. Oh, well, actually it's here, even though it's not linked. Learn.uci.edu. Remember, no late homework accepted. I always emphasize that, and I always get, 10, 20 people asking me to please take, accept their late homework because of this or that reason. And we never do. We don't take late homework. So make sure you turn it in by the deadline. You may discuss homework problems with your friends as long as you're participating actively and learning and not just copying. It's detrimental for you not to do the homework problems on your own. The points that you earn by, say, for example, if you decide to copy the homework or you get a hold of the solutions, which is always possible in today's world, and to get the 7.5%, you're actually hurting yourself big time, because when it comes to do the problems on the exam, you can't do them, right? So the homework problem is really a practice set of problems that builds up on the lecture material. Any questions so far with any of this? Let me actually show you. There is an outline also on the on this syllabus that is online, that is on the EEE website, and it has a breakdown, essentially pretty much almost by lecture. But I want to show you actually this one. We actually breaks up the course in 3 fundamental blocks. So the 10 weeks we're going to spend looking at fluid mechanics will be broken down more or less like this. There is a first part that, of course, includes an introduction, then fluid statics and elementary fluid dynamics. More or less, that's the material that will go into the first midterm. Not exactly like that, but more or less gives you an idea. Then the second block is kinematics, control volume analysis, and differential analysis. And again, that would be the material that more or less would fit into the second midterm. And then finally, the last part of the course, even though it's just 2 topics, potential flow and viscous flows, they're actually lengthy topics that will occupy the last, say, three weeks or so of the course. Again, if you want to see a more detailed breakdown, you have it on the website with the syllabus. Still no questions? Yes? If you want to upload it after the first time, can you do that? Or can you upload more than once after the first time? You can only upload it once. Right? It only takes 1 upload. Yeah. So make sure it's right when you upload it. Yes?
Are you going to be doing mostly like a slideshow, or are you going to use the whiteboard as well?
I won't use the whiteboard.
Okay.
I will write, as you know, but I will write here. It's a lot more convenient for such a large audience to write here than to write on the board. Another thing, many of you really like the fact that you had the lectures online. They're also being recorded this time. So the fluid lectures are going to be available online. If there is something that you missed, you didn't understand, you didn't want to ask me here, you can always go back and watch the lectures online. The website is already up. If you already tried, because there is a link to the playlist on EEE, and you tried, it says private. A couple of you tried that? No, somebody sent me a message that they wanted access, and I said, well, you'll have access after today. So after today's lecture, whenever this lecture is uploaded, it might not happen today, but it might happen on Monday. It should hopefully happen on Monday. This lecture will be uploaded. You will also see the next 3 lectures there. So you'll see today's lecture, and then the lectures for next week, Monday, Wednesday, and Friday, are going to be uploaded as soon as this one gets uploaded. The reason for that is that I won't be here next week. So you don't have to come to lecture next week. Happiness all around. But rather than having somebody else give the lectures, we have pre-recorded the lectures for you, and you can access them online. Make sure you do watch them, though, because obviously you will fall behind if you don't watch those 3 lectures for next week. Again, discussion section is happening on Monday, but the lectures for Monday, Wednesday, and Friday will be online. Then following week, I'll be here. I won't be away anymore. So we'll have the regular lectures. Make sure you buy an eye clicker. Anybody doesn't have an eye clicker at this point? Transfer students, probably. Right? So get an eye clicker, learn how to use it, and then you'll see that I ask these questions. Those who were in Thermo know about it. I ask random questions about sometimes the current lecture, sometimes about the previous lecture, sometimes about things that I think you should know that have to do with fluids. And then you get points for participating.
Are there any course books on reserve at the library?
Yes, thank you for asking. This time I remember to do it ahead of time. So I already asked the library about 2 or 3 weeks ago to put the text on reserve. So it should be on the 2-hour reserve at the science library. So again, if you just want to do that and get your problems that way, that's fine. Okay, so why don't we start with this material. How are we doing on time here? Okay, so we have about maybe a half an hour or so. Let me switch here to the computer and start by showing you this statement. It's already a pretty old statement. It's from January 1997 in Scientific American. Parviz Moin and John Kim are professors at Caltech, and they wrote this article about fluid mechanics in general, more or less to a general audience, since that's Scientific American. And it's kind of a nice way to make you aware of the fact that fluid mechanics is so important. Right? So essentially, if you think about your everyday life, it's fluid mechanics all over the place. You're about to drink a fluid that has a pretty weird color.
Just eat.
Fluid mechanics is in the air that we breathe in. The motion of the air that goes into our lungs. You can study it with fluid mechanics. If you go to engineering applications having to do, for example, flying an airplane, the drag on an airplane, the lift on an airplane, anything that is moving through a fluid, which many engineering applications imply devices that are moving through fluids. Combustion chambers, you're mixing air with a fuel, mixing it up. That's a very important fluid mechanics problem, that mixing process of the reactants that are going to give you the power for your engine. So many things. And here's some pictures of some examples. Very different scales involving fluid mechanics. You go to the largest one on the top right, the Earth, weather, very large scale fluid mechanics. You go to the smallest scale, at least in this set of pictures, would be this one, the bottom on the right. Does anybody know what that might be?
Aneurysm.
An aneurysm. So, so this is an artery, for example, and there is an imperfection of some sort on the wall of the artery. It gets weakened. The fluid motion has a lot to do with it, meaning, of course, the blood flow through that artery. The solid mechanics of the actual artery wall, of course, are important. So that interaction between the fluid mechanics and the solid mechanics of the artery wall might produce an aneurysm. And if you don't take care of it, it'll kill you. And so, and then other intermediate scales, you see the ocean motion, interaction of the ocean with the atmosphere. And probably what looks like an exhaust, maybe an inside of a rocket engine plume in the bottom left. So hopefully what you learn in an introductory class like this will give you some tools to begin to understand and analyze problems that involve some of these situations. But the next question would be to ask you, and I'll switch back to the document camera here, would be to ask you, what is a fluid? What is a fluid? What is a fluid? How would you define a fluid in very simple terms? If you raise your hand, I'll ask you. If not, I'll point to somebody. Yes? Something that flows. Okay. That is not a solid. All right. Is a gas a fluid?
Yes.
Yes. So in everyday life, we think of fluid as a liquid. If you ask randomly somebody on the street about a fluid, they'll think of a liquid. Of course, you know that. You know better than that. Fluids, when we talk about fluids, we mean either a gas or a liquid. There is a more precise definition. A substance that deforms continuously when acted on by a shearing stress of any size. So, a couple of keywords here. Well, deformation, somebody mentioned that, something that flows. But there is deformation. However, a solid can also deform. So one of the key differences is this continuously. So it continuously deforms when there is a shearing stress acting on it. You know what a stress is? What is a stress? Define a stress for me. Right here. What is a stress? Don't look at him, he doesn't know. What is a stress? A force per unit area. That's in general how we define it in engineering. So when we say a stress here, we mean force per unit area. And what is a shearing stress? If it's not shearing, which other type of stress could we be having? Not emotional stress, of course, which you have a lot of right now. Huh? Tensile or normal, right? So what is a shearing stress then? How do you define it very easily? No, that's the tensile. If it's negative tensile, it'll be a push, right? Tensile, you're pulling or pushing.
Parallels to the plane of the area you're playing.
There you go. That's a very precise definition. Parallel to the plane of the area that we were just talking about when we said force per unit area. So a shearing stress on a surface is parallel to that surface, whereas a normal stress would be perpendicular to that surface. It could be tensile if it's, we think of it as pulling. It could be compressive if it's into, but it's normal. So you either have a normal stress or a shearing stress. So here, the one that we really care about is the shearing stress. So it says that this substance that we call a fluid will continuously deform as long as there is a shearing stress acting on it. And the final keyword is of any size. Does anybody know why we put that there, of any size? There's a reason for that last part of the sentence, of any size. Anybody? Nobody? Yes?
Would it just not be a fluid anymore if there was a force acted on it and it didn't move?
There is a force acting on it and it doesn't move continuously. Yeah, it might not be a fluid, it might be a solid. But the any size is that it really, sometimes you see that replaced by shearing stress. Doesn't matter how small, however small it is. So you can have the shear stress, say make it smaller and smaller, and see if this thing still deforms, and it will continuously deform if it is a fluid. So if it is a fluid, it doesn't matter how small it is. Mathematically, we would say even if it's an infinitesimal stress, a shearing stress, if it's an infinitesimal shearing stress acting on that surface, the fluid will continue to deform. Right? So that's why we say of any size there. All right, so here's a little picture of what's going on. So stress, force per unit area, you will never again forget that, right? So here is a simple experiment that I could think of. I could put a fluid, something that I think is a fluid, between two planes. So I think that I build a little flat channel, two parallel plates. I keep one fixed, and I put the fluid in between the two planes, and I move the top one like you see there with the red arrow. It's moving to the right because I want to shear that fluid. I want to apply a stress that is tangential to that plane where it's acting. So obviously, if I do that, then this fluid that is in this gap will move in some form that we're going to determine as we learn fluid mechanics. But that would be a way. And then I can make my stress any size that I want. I can make it larger, smaller. I can make it very, very, very small. And as long as I see that there is some flow motion there, then we call that a fluid. There are some minor exceptions to this. There are some particular types of fluids that we still call them fluids and behave a little bit differently, but we'll talk about those later. All right, so here we are trying to solve a fluid mechanics problem. Think of any of the problems that I had in the pictures. You're trying to solve the problem of motion, say of a storm somewhere above the ocean or on the ocean, or you want to solve the aneurysm problem. You want to study the fluid mechanics. So if you are doing that, if you want to solve this problem in fluid mechanics, then you have to ask yourself, well, what do here's a problem in fluid mechanics I want to solve, but what should I be looking for in terms of solving? What do I want my fluid to satisfy? In terms of the physics and the mathematics of that fluid. Because these are laws that you can almost uniformly think of them in any branch of physics or therefore engineering. So he's drinking this fluid. Now he's gone about 90% of the bottle, of the liquid that was in the bottle is now somewhere else. No, you started okay.
Conservation of mass.
Conservation of mass, right? So if he's solving a fluid mechanics problem of the fluid coming from the bottle out into his mouth and then down his throat into his stomach, and there is conservation of mass. That's one thing you need to account for. So one of the things that we worry about is making sure when you're solving a problem in fluid mechanics is that mass is conserved. The fluid that disappeared from some place must be somewhere else. What else?
Momentum.
What about momentum?
Conserved.
Is momentum always conserved? And that's a tricky question.
Angular momentum.
No, you're making your life too complicated. Let's stay within linear momentum. Is linear momentum conserved? Always? Not always. Why?
Elasticity.
No, you're making it complicated too. Not because of elasticity.
Friction.
Well, what is friction? A force. So really, Newton's second law, right? Linear momentum of a system would be conserved if what? Well, more than just friction. A force, external forces somewhere back there, right? If there are no external forces acting on my system, then of course you'll conserve linear momentum because that's what Newton's second law. So really we refer to it as Newton's second law. Now the reason I said it was tricky is because we always end up still in some situations calling it conservation of momentum. So there is this kind of analogy when people think of Newton's second law and conservation of momentum. And you will probably hear me here a couple of times refer to an equation that will come out of Newton's second law as a conservation of momentum equation. Even though that conservation of momentum equation is probably telling you that momentum is not conserved. Because if there are forces acting on the system, then but for now, let's just call it Newton's second law also because that's very obvious to you. You just took dynamics very recently within the last year or so. So Newton's second law is fresh in your minds. What else should I worry about when I'm solving a fluids problem?
Bernoulli.
Hmm?
Bernoulli.
I don't know anything about Bernoulli. Who is Bernoulli?
Guy who knows a lot about fluids.
Oh, no, we don't know anything about Bernoulli yet.
Energy?
Yes, what about energy?
That's to conserve.
Okay. Well, do we have another name for that? Law of conservation of energy? Another name? Rewind 1/4? First law of thermodynamics, right? So the first law of thermodynamics is an equation of conservation of energy, right? So we have a fluid mechanics problem. We worry about conservation of mass. We worry about Newton's second law. We worry about conservation of energy, or the first law of thermodynamics. Anything else? Yeah, we might as well satisfy the second law too, since we also know about it. So you would throw in second law of thermodynamics. So this is a very general picture of the fundamental laws of physics that we need to be thinking of when we're trying to solve a fluid mechanics problem. Of course, like I said, this is a very general picture. There'll be many details that we will have to worry about too. And I'm just going to show you a few here. So other things that we'll have to worry about are things like fluid properties. Many of these are, or you should be very familiar with because you've seen them before, right? When dealing with a fluid problem, most likely you will have to know something about its density. You know everything about density. Specific volume, again, rewind to thermodynamics, is nothing but the inverse of the density. A few other things that you might see when you're talking about fluid mechanics, the specific weight. Nothing but the product of the density times the acceleration of gravity. That's we refer to it as a specific weight in fluid mechanics. What about specific gravity? Has anybody heard about specific gravity? What is specific gravity? Nobody? Have you heard about specific gravity?
Yeah.
But don't remember what it is. Anybody? Huh? No, it's not the inverse. Good guess. It's not the inverse of gravity.
The density divided by the density of water.
Of?
Water.
Of water. Very good. Yeah. So that's a very specific, unless you remember like he did, I'm sure you have seen it. Specific gravity is just a comparison of the density of the fluid with respect to some standard value, and that standard value is taken to be the density of water at normal conditions. So we call that the specific gravity. It's just to give you an idea of how much denser that substance, that fluid is compared to water. All right, so from thermodynamics, we also knew this. From equilibrium thermodynamics, the density is a function of how many properties in equilibrium thermodynamics? 2 properties. And there was a condition for those 2 properties. Who remembers what condition we imposed on the 2 properties? Huh? Not extensive, but the opposite. Intensive. And what else? There was another condition. The one that people usually forget after they finish thermal. Anybody? They have to be intensive and they have to be independent. meaning that they cannot be linked to each other in any way. And there was only one situation, one scenario where you had to worry about properties being linked. Is that ringing a bell? What? Not ringing a bell? When we had a mixture of liquid and vapor in the dome, then properties of pressure and temperature were linked. So you thought you could forget all about thermodynamics, but you can't. So I have picked here temperature and pressure, which of course would imply that I am not in a two-phase region, because if I were in a two-phase region, then pressure and temperature would be linked to each other, and I couldn't pick those two to define the density. I had to pick something else. But since we're in introduction to fluid mechanics, then we're not going to be dealing with mixtures. We're either going to be dealing with a vapor or a gas or a liquid, and therefore we won't have that problem. So if you have a pure liquid or a pure vapor, then I can use temperature and pressure as my two independent intensive properties. And because those are the most common ones, then usually we use those when we're defining a density or any other property of the fluid. So what is the density of water under normal conditions? What is the density of the liquid you just drank?
1,000 kilograms over 1 cubic meter.
Very good. 1,000 kilograms per cubic meter. That's about the typical value of, assuming that that was water that you were drinking there and not oil. Right? So normal conditions, which means 1 atmosphere, 300 Kelvin, about 1,000 kilograms per cubic meter. Another one that you should always remember is air. This air in the room under standard conditions, about 1.2 kilograms per cubic meter. Because you have to know those values. As an engineer, you have to know. As a mechanical or an aerospace engineer, you shouldn't have to look it up, right? The density of these two fluids. And then I threw in here, of course, one connection between properties that we learned in thermodynamics. It's not the only one, but it's perhaps the most commonly used one for a gas, which is the ideal gas law. So that, of course, is a connection between density and pressure and temperature. So this is simply an example of any relationship between density and two other properties. Okay, any questions so far? Okay, another property that you think is important. For fluid mechanics, very important, viscosity. Why is viscosity so important in fluid mechanics? It affects very significantly the flow rate that we were talking about at the beginning in the definition of a fluid. That's why viscosity is so important. So it's sort of and you'll see exactly what the relationship is, but it has a very direct effect on the rate at which that fluid is moving. Let me go back here to the computer for a second. Let me minimize this. Okay, let's see. I think it's this one. All right, so let me show you this video to illustrate a point that I want to make next. So here is a channel. There is going to be a fluid moving. I forget if it's from right to left or from left to right, but we're going to find out as soon as I play the movie. And that little thing that you see there, that's vertical black line, is just a device that allows you to inject a dye at any point within the flow field. So by injecting a dye, you're essentially using it as a marker. So you're putting a marker, and the motion of the die, because otherwise you wouldn't be able to know what the fluid is doing. The motion of the die will give you a very good idea of what the fluid is doing. So here it has been moved all the way to the bottom. I don't know if you can see there is a faint horizontal line. Yeah, you can see it there. Right? A very faint horizontal line. It's kind of hard to see there. But that's sort of what gives you the three-dimensional perspective of what we're looking at. So here this injector has been put all the way to the bottom, almost touching the bottom surface. And it's injecting this dye. Okay? So you can see how it injected some at the bottom, and now we're moving it up. And as we move it up, we get a good sense of what the velocity of the fluid is, some sense, because we can see this trace of the marker fluid. But the point that I want to make is see what happens at the bottom, right? The dye that was injected at the very bottom, touching the surface, is not going anywhere. Right? Seems to be stuck there. The flow is still going. So only when we come in with some other stirrer and move it around, then it gets washed away. The fluid was always moving at all times. So what's going on there? What's going on there? What you saw there in that video is what we know in fluid mechanics as the no-slip condition. So essentially, it's telling you, what the no-slip condition is telling us is that the fluid that is in contact with a surface will have the velocity of that surface. In this case, the bottom surface was not moving, so therefore the fluid that is in contact with that bottom surface is not moving. That's a no-slip condition. And it's a well-verified fact that fluids will do that. So if I have flow over a wing, then the fluid that is touching the wing is not moving with respect to the wing, right at the point of contact. And we know that as the no-slip condition. So that's what we saw. This is a little different of a setup, but we're going to use this condition, the so-called no-slip condition, to finally get a connection between viscosity and the fluid motion. So here is not exactly the same experiment that we saw in the video, because on the video we didn't see a top wall. There was a wall at the bottom, but there was nothing really that we could see on the top. I'm going to add that top wall, like I did in the first diagram that I showed you when I was trying to show you the meaning of the shear stress acting on the fluid. So here I have a bottom wall is fixed, and then I have a top wall that I'm going to move at will. So by applying a force, which you can see here in red, by applying that force, I will be able to move that top plate with a constant velocity. So I'll move with a constant velocity that I'm calling capital U. So if I do that, we know from experience that the fluid in the gap is going to move from left to right. And because we know about the no-slip condition, then we know that the fluid at the very bottom, because that plane is fixed, is not going to go anywhere. So the fluid at the very bottom sticks to the bottom. The fluid that is touching the top plate sticks to that plate, and therefore it's going to move to the right. So I have no motion at the bottom, and I have a motion characterized by the velocity capital U at the top. And of course, something will happen in between. The fluid in between will move with some velocity value that is somewhere between 0 and capital U. But so let's say that I do this for a very short instant of time. So I just slide and I just capture what happens in a small dt, differential time. I can of course say that the top plate will move a distance dx, which will just simply the product of the velocity times the interval of time. So the product of u dt will give me the displacement of the top plate, and therefore the displacement of the top fluid. Right? Then I can write an expression for the tangent of that angle that forms there, the angle that I call d beta. Its tangent is, of course, the opposite side, which is dx, divided by the adjacent side, which is h. H is the gap between the two plates. So I know the tangent of d beta is dx over h. And of course, I am saying that that's approximately equal to the angle itself. Why do I say that? Because d beta, the angle itself, is very small, because I'm only allowing for a small dx. So of course, that's an exaggerated sketch. But because the angle is small, then the tangent is approximately equal to the angle itself. Anyways, dx over h. So what about if I measure now the angular velocity? So the rate at which beta is changing, d beta dt, all I need to do is divide my expression by dt. So dx over h divided by dt. And of course, dx over dt is u. So in a very simple way, I am showing that this angle that is swept by the fluid, right, as it moves from left to right, this angle d beta, its rate of increase, d beta dt, so its angular velocity, is equal to the velocity at the top divided by the vertical distance. That's a very important quantity in fluid mechanics. We call that the shear strain rate, because that's a quantitative measure of the flow that we were talking about earlier. When I shear a fluid, it will flow. How do I quantify that flow? The best way to quantify it is by measuring these so-called shear strain rates. So I have a shear strain rate, which is the angle variation in time, d beta dt, and that is u over h. What are the units of a shear strain rate? Where did the Pascal come from? What are the units? 1 over second, right? 1 over second. Why 1 over second and not Pascal? Where did Pascal come from?
Because it's shear strain, right?
U over h,
Oh, yeah.
right? Meters per second divided by meters. So 1 over second. The units of shear strain rate, which is a repeat, is a very important quantity in fluid mechanics. The shear strain rate is 1 over second. Remember, it's d beta dt, right? The angle beta has no units or radians per second, right? So the angular variation is like an angular velocity, what we're measuring, right? d beta dt is an angular velocity, so therefore it has units of 1 over second. All right, now I can make the approximation that u over h is really the slope of that dashed line that you see going from the bottom to the top. This line that was here vertical and now it's over here, right? This dashed line here, that's like the slope of the that curve. Right? If I approximate it as a straight line, which I will do, I will approximate this dashed line as a straight line. And therefore, I can say that u over h is just the slope, du dy. The reason I'm doing that is because I don't want to have a shear strain rate that is just for the top. I want to find it anywhere in the fluid. So all I need to do, if I'm looking at a small portion of a fluid that's moving, all I need to do is I can do it and say, think about it or actually quantify it. But if I'm looking at a small fluid element, all I want to know is how much the velocity is changing, say from top to bottom. That gives me the delta u or the du, right? And then measure that vertical gap, right? That gives me the slope of that motion. And that gives me a measure of the shear strain rate. The difference in velocity between the top and the bottom divided by the distance between the top and the bottom is the measure, is the slope or of the shear strain rate. So that will be a very important quantity for us. But we still have to make the connection between this and viscosity. So let's go back now to the shear stress. You were thinking about Pascal, so This is now shear stress. Do not confuse shear strain rate, which is what we just measured, with the shear stress that we were talking at the beginning of the lecture, which is the force per unit area. Two different things, but they're going to be connected now. So the shear stress, I go back to this schematic of the two plates. I put the area there, so I drew it in perspective so you can see the area here. The area A, that's the area that I'm using to measure the stress. So I have a force. I pull the top plate with a force F to the right. If I divide the force by the area, then I get the shear stress. So that's my shear stress. And then, of course, you also have here the same schematic of the fluid moving in the gap. Zero motion at the bottom, maximum velocity at the top, and then what for now we'll just draw as a straight line. It won't always be a straight line, but so the connection between this shear stress and the shear strain rate that we just looked at in the previous page will be an important one. Shear stress, shear strain rate. How are those two connected to each other? One way is the way it is connected for what we call a Newtonian fluid. What is a Newtonian fluid? Does anybody know what a Newtonian fluid is? It has to do with that connection between shear stress and shear strain rate.
It's when you can apply a force to a fluid and then it becomes a solid.
Nah, way too complicated. It's a linear connection between the two. So, here is my shear stress, tau. Here is my strain rate, shear strain rate, du dy. If this connection between the two is through a constant of proportionality, so it's a linear connection, then that's what we call a Newtonian fluid. The shear stress is linearly proportional to the strain rate. In words, shear stress linearly proportional to the shear strain rate. Okay, so if it's proportional, there must be a constant of proportionality between the two. And if you're putting things together as you're listening to me, you know what that constant of proportionality is. What is the constant of proportionality between shear stress and shear strain rate? It is the viscosity. Right? So the viscosity, we also refer to it as dynamic viscosity, because there will be another viscosity that we'll talk about. So the so-called dynamic viscosity is the constant of proportionality, and therefore the relationship that I'm looking for is right there. Shear stress equals to viscosity, which is the constant of proportionality, times shear strain rate du dy. If a fluid satisfies that law, follows the behavior described by this law, we call it a Newtonian fluid. Very easy. It'll get more complicated. What are the units of this viscosity? You can bring Pascal. You're not going to bring your friend Pascal in now. What are the units of viscosity? Well, from that relationship, I can simply say, right, viscosity is the shear stress divided by the shear strain rate. The shear stress is newtons per meter square, which of course is Pascal. Well, I'm not using it here. Newtons over meter squared divided by the shear strain, which is 1/2. Simplify everything. And it turns out that you can write it two ways. You can write it as newtons times second divided by meter squared, or by decomposing the newton is just kilograms over meter per second. You should remember at least one of the two, whatever is easiest for you to remember, so that you don't have to keep looking it up. Units of viscosity. Pick one of the two that you want to remember and work with that. Those are the units of viscosity. Now, I told you there was another viscosity. Remember the top one, mu, Greek letter mu, is called dynamic viscosity. There is another one called kinematic viscosity. Anybody knows what kinematic viscosity is?
The dynamic viscosity over the density of fluid.
Very good. How do you know that?
I don't remember.
Okay, I don't care either. Kinematic viscosity, he very well said it, is dynamic viscosity over the density of the fluid. Just a definition. It becomes handy in some problems to work with the kinematic viscosity. So if you want the units of kinematic viscosity, you of course divide units of viscosity by units of density. Simplify everything down, it comes to meters squared per second. Kinematic viscosity. And the name dynamic viscosity versus kinematic viscosity is because of the units. So kinematic viscosity doesn't have a kilogram or a Newton in it. It only has kinematic quantities. Dynamic viscosity has a Newton in there or a kilogram in there. That's therefore the name dynamic versus kinematic. Okay, I'm out of time. Remember, watch the lectures online. Come to discussion on Monday. And I'll see you again in 1 week.